All right, so we're going today looking at compressed gases. So if you go back to Monday's lecture, Monday we spent most of the time talking about flammable liquids and all of the different definitions of flammability according to the Department of Transportation, the NFPA, and now we're going to kind of look at gases. And we can start with just kind of some general definitions. By definition, a compressed gas is simply a gas that has been confined under pressure. So normal pressure is about 14.7 psi. A compressed gas would be a gas that is held at a higher pressure than that. And how much higher than that depends upon the nature of the tank that it's stored in and a whole bunch of other factors like the size of the tank and so on. Some common examples: compressed hydrogen, compressed oxygen, compressed nitrogen. So things that you might buy from an air gas supplier, things that you might find in an anesthesiologist's purview. Those would certainly qualify as compressed gases. Liquefied compressed gases, this comes back to what we were talking about last week with phase diagrams, where if we hit a certain pressure point, we will actually see the gas liquefy instead of just raise up in its pressure. And that liquefaction ends up resulting in a substance, a material that is far easier to transport, and we can generally put a whole heck of a lot more of it into the container than otherwise because it liquefies. So it doesn't require nearly as much space. It's been compressed down to the point of becoming a liquid. And the most common examples of these are liquefied methane, or certainly what you're probably most familiar with, propane. Now, in either case, one of the measurements that we have to kind of tell us how much gas is contained in a container is by using its gauge pressure. Now, the gauge pressure of a gas is measured using a pressure gauge, no shock there. But what that pressure gauge does is it measures the pressure above atmospheric pressure. So when we have a gauge pressure of 150 psi, what that psi gauge is saying is that the pressure inside of that cylinder is 150 psi above atmospheric pressure. So if I want to know the true pressure of the compressed gas, I would need to take that gauge pressure, 150, and add to it 14.7 psi, which means that the total pressure inside of that particular container would be 164.7 psi. And this is important to note because, again, going back to what we were talking about at the end of Monday's lecture about the hazards associated with empty tanks. If your gauge pressure is reading 0 psi, again, that doesn't mean that the tank is devoid and empty of everything. What it means is that there is 1 atmosphere's worth of pressure still in there. And depending upon what that substance was, all of the hazards of that substance still apply. So if you have 1 atmosphere's worth of methane, then you've got 1 atmosphere's worth of flammable goods. If you've got an empty cylinder of carbon monoxide, then you've got 1 atmosphere's worth of carbon monoxide. That's enough to asphyxiate you. So when we look at, quote, empty tanks, what we have to understand is that there is still 14.7 psi of whatever that gas is still in there. And so we still need to treat the empty container with the same precaution that we treated it when it was full. So let's take a look at an example of the relationship between gauge pressure and absolute. So we are told that a gas is compressed with an absolute pressure of 486 psi. The question is, what will the pressure gauge read for this particular tank? Yeah, go ahead. It is not. So again, this is where it's important to know our definitions. Absolute pressure would include gauge plus atmospheric. So if I want just the gauge, I would need to subtract out the atmospheric. So 486 psi minus 14.7 psi would give me 471.3. Thank you. And so my pressure gauge would give me that reading. It would say 471 or 472 psi. So this is important to note, again, just because understanding what that gauge is actually telling us. So when we've got a regulator on an acetylene tank, that regulator and the pressure gauge on it tell us how much extra we have. And when that goes down to 0, again, it means that we are out of excess. No more is going to come out, but we're going to still have an atmosphere's worth, 14.7 psi worth inside the tank still. Now, as far as ways that we can store compressed gases and compressed liquefied gases, there are a variety of ways for doing that. You may have seen this kind of one. This is a spherical high pressure storage tank. We tend to see it more for like industrial kinds of storage, large scale storage at factories or energy plants or things like that. Let's look at some more definitions. So OSHA, Occupational Safety and Health Administration, they define a compressed gas as any gas confined to a container at an absolute pressure exceeding 40 psi at 80 degrees Fahrenheit. Or a gas or mixture of gases with an absolute pressure exceeding 104 psi at 130 Fahrenheit, regardless of what the pressure might be at 70. Or this third definition, a liquid having a vapor pressure above 40 psi at 100 Fahrenheit. And remember, we saw this definition when we were talking about the definition of a flammable liquid. And the reason we saw that is we said, well, the reason we have the threshold of 40 psi at 100 Fahrenheit is because if it goes above 40 psi, then we're talking about a gas. Now these PSIAs, that's basically their absolute pressures. So you will sometimes see letters attached to the pressure unit. And if there is an A on it, that is talking about absolute pressure. If there is a G on it, then it's talking about the gauge pressure instead. And so, again, a really good reason to know the difference between the two terms. So, if you do a little bit of quick math here, then a compressed gas needs to only have a gauge pressure of about 26 psi. Below that value, we don't consider it a compressed gas. It's just a confined gas. So pressurized tanks that are near the end of their life kind of dip down below that definition as we bleed out those last few milliliters of gas. Department of Transportation labels a gas as flammable if that gas is a gas at 68 Fahrenheit or less and at normal pressure. And one of the two things below are true. If this gas is ignitable at a 13% or less mixture, so if we go back to our terms from Monday, what we're talking about here is LEL, the lower explosive limit. If this gas ignites at a concentration of 13% or less, it is considered flammable. Or it has a flammability range of at least 12%. And remember, we can get the range by calculating the upper limit minus the lower limit. So this first definition here about the temperature and pressure is really just about defining what a gas is. So at room temperature conditions, at normal atmospheric pressure, this substance is a gas. Seems relatively straightforward. So this is to help us kind of exclude it from that class of liquids that vaporize at slightly elevated temperatures. And then these two represent the flammability standards. Now keep in mind, just because something is classified or is not classified as flammable by the DOT doesn't mean that it won't necessarily ignite. So let's say, for example, that we have something that will ignite at a 20% mixture. So it ignites at 20% and stops being flammable around 30%. Well, that doesn't qualify under this first criterion. And the range is only 10%, so it doesn't qualify under the second one. DOT says that's not a flammable gas. But if you have that gas under those circumstances in that range of flammability, we will see it ignite. The distinction here is about associating level of hazard. That particular gas isn't considered to be flammable because flammability is not of a high concern, given the fact that its flammability range is kind of on the small side. Let you try this one for yourselves here. Ammonia gas has an LEL of 16% and a UEL of 25%. Question is this: can we classify ammonia, NH3, as a flammable gas according to the Department of Transportation guidelines? So going back to our previous slide, in order to be considered a flammable gas, it has to be a gas at room temperature, and it either has to have an LEL less than 13%, I'm getting rained on. Either has an LEL less than 13% or a range greater than 12. So is ammonia a gas at room temperature? Absolutely. You know what ammonia smells like. The only way that you can smell something is if it vaporizes. So it's a gas. Is it flammable? Well, LEL has to be less than 13. 16% doesn't qualify it. So not there. Range has to be greater than 12. If I take 25 minus 16, I only get 9%. So it doesn't qualify there either. So even though ammonia is a flammable material in terms of in this range, it will ignite. And for that reason, when you are using ammonia, and this is true if you are agriculture, use ammonia as a fertilizing agent, and there's all sorts of reasons why. Flammability, you gotta be careful with it, because in your normal usage, you can stumble into that range and cause a fire. So you do have to be careful, but in terms of its transport, you're not going to find ammonia with red placards. You're going to find it with green placards because it's considered to be a non-flammable gas. More classifications from the DOT. So a gas can get a green placard, a non-flammable designation, if that material or mixture exerts in its packaging an absolute pressure of 41 psi or greater at room temperature, and is neither a flammable gas nor a poisonous gas. So if it is a flammable gas, obviously it's going to get a red placard by the DOT. If it is a poisonous gas, it'll get a black and white placard based on the DOT regulations. But if it is neither, and it is at a high enough pressure to be considered a compressed gas, then it'll get one of those green non-flammable placards. To get one of the black and white placards for a poisonous gas, again, it has to qualify as a compressed gas. So the criteria here at the top are exactly the same as the ones that were on the previous slides. The only one that is different is that we will consider the value of pressure at a lower level. So the previous ones, we were talking about 40 psi of absolute pressure. With inhaled toxins, we are talking about 14.7 psi. So literally, if it has a gas in it, even if the gauge pressure is 0, if it has a gas in it, we are considering it to be a toxic gas if one of those two things is true. It is known to be so toxic to humans as to pose a health hazard during its transport, or it is presumed to be toxic based upon tests on laboratory animals. And we'll get into what LC50 means when we talk about toxicity in our toxins unit. But LC50 refers to what is called the lethal concentration, 50%, meaning that in laboratory animals, when a dosage of this amount is given to the laboratory animals, half of them do not survive it. So to be considered a toxic gas, it needs to exist in the gas phase in any amount, basically, up to including 1 atmosphere of pressure. And it either has to be a known toxin or a presumed toxin based upon laboratory testing results. Move off of the DOT now, and let's talk about the Global Harmonized System, the GHS. By definition, GHS says that a compressed gas is any gas that when packed under pressure is entirely gaseous at -58 degrees Celsius with a critical temperature equal to or less than -58 Fahrenheit. I meant Fahrenheit the first time as well. This is to kind of separate the compressed gases from the cryogenic liquids. Remember, with cryogens, we're talking about things that are at cold temperatures and usually high pressures. The GHS, notice, we aren't making any kind of determination about what considers the proper pressure. We're looking just at what phase of matter it is and saying that if it's packed under pressure at all, that is, if the absolute pressure is greater than normal atmospheric pressure, and it's a gas at that temperature, we're going to consider it a compressed gas. Now remember, the GHS system uses kind of that multiplicity of placards instead of the DOT system where we're going to try to give you all the information in one color-coded diamond. The GHS, it might be, we might have the placard for flammability and the placard for being a compressed gas and the placard for being an explosive. We might have a whole bunch of those pictograms all at the same time. And so by that way, we're going to get simpler definitions as a result, because you can stack those placards on top of each other to give the duplicity of all of the different hazards. Let's talk about storage. When it comes to storage, there are a couple of ways that we can store gases safely to avoid potential incidents. And the first thing that we would do in general is we would talk about how we store them. We store gas cylinders in an upright position. We don't store them laying on the ground. We don't store them in carts or dollies. We store them standing up. And we usually try to keep at least 3 points of contact by using walls, straps, or other cylinders to help stabilize the cylinders to each other. And so one of the techniques that we can use to ensure that 3 points of contact is something called nesting. And in nesting, basically what you're going to see is that you're going to line those cylinders up in these neat little rows, and you're going to basically set them up like bowling pins, only they're touching each other. And so if you can imagine there's a wall here, we're going to put those cylinders up against the wall. And so the 3-point contact system, 1 point of contact would be with the wall itself. Another point of contact would be the cylinders to each other. And then a third point of contact would either be the use of some sort of strap to fasten them to the wall, or in the case of having even more cylinders around, placing a second row of cylinders nested in the gaps between the first cylinders. And again, this is where I'm talking about that bowling pin kind of configuration, where we've created a third point of contact between them to help stabilize them. Now, whenever that last row is, you would still want to use some kind of a strap mechanism to secure them to the wall. That is the safest way to store them so that they do not accidentally get tipped over or roll away, or in the case of some sort of industrial accident, something bashes into them, they don't all fall over like bowling pins. So that minimizes the damage. So that's the technique of nesting. The technique of grounding involves when we are dealing specifically with flammable materials, connecting them to each other and connecting that group of cylinders to the ground to help dissipate electrical charge when it were to occur. So let's say that there's a power surge that goes through the building, wave of electricity goes through, it touches one cylinder in particular, that electrical energy could be enough to spark a fire inside of it if it were flammable. But if that cylinder is bonded to a series of other cylinders and it all eventually goes into the earth ground, then that electrical energy gets dissipated over all of them and eventually goes into a neutral dumping ground, basically, and the damage is minimized. So here's an example. This is a rack-like cage. So this is one way that you can store compressed gases, is using an external cage like this. And so in the place of a strap, basically you've got a door that closes there to keep them contained. There are other means that are similar. So in the event, so you can see flammable materials as designated by these red cylinders. These are usually kept apart from non-flammables as a general safety precaution. And you can see, again, we've got a cage here for this outdoor facility to help keep them separate. The third storage technique I've already talked about, actually, bonding, is the connecting of multiple cylinders to each other to help dissipate that electrical charge. So if a spark comes off, or if you're using like an arc welder and one of those electrical arcs gets loose, gets away from you, goes out. If it were to encounter one of these metal cylinders, that electrical charge, again, could do some pretty significant damage depending upon the nature of the substance. But if we bond together those cylinders to each other, it dissipates that electrical energy. And the dissipation of that electrical energy is going to result in a much less significant danger than before. And again, usually we see grounding and bonding done together. So we bond together all of the cylinders using just wires, wire clips. And then the last one gets connected to the earth ground so that all that electrical energy just gets dumped into a safe location. Some other storage techniques and guidelines, kind of goes without saying, when you are moving a cylinder, you want to try to move it in such a way to avoid damaging it. Damaged cylinders can leak. They can become unreliable. You certainly don't want to use them. Storing them in an upright position using those techniques that we described are important. When you're not using the gas cylinder, putting on that protective cap so as to protect the nozzle is really important. That means, of course, that you have to disassemble the gauge regulator so that you can store it properly. But that protective valve actually protects the most vulnerable part of the cylinder, and that's where you turn it on and off. That part is made out of the thinnest metal because it's a valve screw and can break off the most easily in the event of a dangerous or accidental kind of situation. And I'll say the last one here, I mean, the third one there, in general practice, can be difficult to remember to do every time because you get used to working with something and you're like, all right, taking off this regulator, taking off the pressure gauge and putting it away properly takes a ton of time. And then I got to spend all that time putting it back together the next day. It'll be fine. I'm coming back to it tomorrow anyway. That happens. Shouldn't, but it does. That's kind of reality. This last one's also something that happens often. I need to switch out my gas tank. So I go get one off of the wall there, and I just kind of pick it up off the wall, tilt it onto its side, and roll it to wherever I need it to go. Set it down, I'm good. Well, unfortunately, that's not the most safe way to do things, because if it rolls away, gets away from you, now you've got a very large, heavy gas cylinder rolling away, and by the way, it's going to crash onto the concrete floor. Who knows what's going to happen when it does. So when you move a cylinder from one area to another, you're supposed to put it on a dolly, on a cart. Usually the cart has a chain on it of some kind to prevent the cylinder from going away. Inside the gas cylinders themselves, there are two pressure relief devices available. Their primary purpose is to help release the gas inside safely so that in the event of an emergency, you don't have a catastrophe. And what I mean by that is, if you are talking about a flammable gas, for example, and it's compressed inside of this cylinder, and there's a fire going on around it. Well, we know from our gas laws that as the temperature of a gas increases, so does its pressure. And if the pressure becomes too great on the inside, it'll basically burst that tank. And the result is going to be a massive explosion, a giant fireball, and a ton of damage. What these pressure relief devices do is when they encounter certain temperature or pressure circumstances, they will open a door inside of the gas cylinder to allow the gas to escape out slowly. And by allowing that gas to escape out slowly, it'll prevent the potential harm of something more significant, larger explosion. So the two pressure release devices are these. First is called a fusible plug. The fusible plug will melt at a particular temperature, and it will open up a pathway for the gas inside of the cylinder to get outside of the cylinder. Now, that particular temperature is considerably higher than room temperature. Again, it really only gets activated in the event of a significant fire. Same thing with rupture discs. They're made out of metal. They exist inside of the regulator head, inside of the valve. And when the pressure inside of the tank gets to be too high, it bursts. It breaks open. And again, it allows a pathway for the gas to get outside of the tank and allow the pressure inside of the tank to remain at a safe level. And so you can see both of these devices are held inside of the top part of the top part here next to the nozzle, next to the valve. The fusible plug is usually down here. Notice again, it is lower than where the normal screw valve comes in, because the idea is that when that plug breaks, the gas can just travel out through that small hole slowly, and the pressure gets released. And then same basic idea for the frangible disc as well. It exists in a place where even if the cylinder is closed, the gas can still get out and get out safely. So that's all that we have for today. On Friday, we will finish up chapter 3. We'll talk about the last little bits of flammable liquids and gases. And I'll send you off to lab. Have a great afternoon.